All right, we're going to wrap up chapter 3 talking about the hyperbolic functions, which is something we've never talked about before. So this will be exciting to learn something brand new. Okay, so if you look at, if you do enough math and engineering and type things, then there are certain combinations of the exponential functions e to the x and e to the negative x that arise quite frequently. And they happen so often that they're given special names. Now they could have picked any name, but it turns out that these functions are analogous to the trig functions that we know and love. And they have the same relationship to the hyperbola that the trig functions that we're used to have to the circle, like the unit circle. So they are called hyperbolic functions, and they use the same kind of sine, cosine, tangent kind of notation, but the h at the end signifies that these are the hyperbolic functions. So this is the hyperbolic sine, the hyperbolic cosine, the hyperbolic tangent, and so on and so forth. Now these two we pronounce sinh and cosh. I don't know that the other ones are pronounced that much. Probably just say hyperbolic tangent, hyperbolic cosecant, and hyperbolic secant. But usually those are shortened. And sinh is kind of a funny thing because there's not a ch at the end, and we don't just say sin or anything like that. So it's just sinh. All right. So we're going to look at these hyperbolic functions. Notice that the sine and the cosine are the only ones, or the hyperbolic sine and hyperbolic cosine are the only ones that are defined in terms of e to the x and e to the negative x. All of the rest of them are defined in terms of the hyperbolic sine and hyperbolic cosine. I mean, we could write out expressions in terms of the exponentials, but usually these are just defined in terms of the hyperbolic sine and cosine. So notice they're analogous to the trig functions. The hyperbolic sine over hyperbolic cosine will be the hyperbolic tangent, and then the reciprocal of that will be the hyperbolic cotangent. Okay, the reciprocal of hyperbolic sine is hyperbolic cosecant. The reciprocal of hyperbolic cosine is hyperbolic secant. So they're very similar to the trig functions that we know. Okay, so if we think about the trig functions, sometimes we call them the circular trigonometric functions to differentiate them from the hyperbolic trigonometric functions that we're looking at now. So we know from trigonometry and even from the work that we've done in algebra that the unit circle is closely related to the trigonometric functions, right? So if I have the unit circle here, so that's the circle with radius 1, I see that radius of 1 right here in this triangle. Okay, so I can pick any point on the circle, and if I look at the x-coordinate of that point, okay, that x-coordinate will be the distance from the origin to the x-coordinate. Okay, and so if this angle right here is t, if we took the cosine of t, we would get that x distance, that's the adjacent, over the hypotenuse of 1, or just x. So the x value of a coordinate on that circle will just be the cosine of t. And if I look at the y coordinate, okay, well, y is the length of that side. Okay, so if I think about the sine of the angle t, well, that's going to be opposite, which is y, over hypotenuse of 1. So y is really just the same thing as the sine of t, right? So every single point on the circle, okay, if I pick some angle t, I can find the coordinates of that point are going to be cosine of the angle for the x-coordinate and sine of that angle for the y-coordinate. Now, we know that the equation for a circle is x squared plus y squared equals the radius squared, which is 1 squared in this point. In this case. And now, since x is cosine of t. We could substitute that in there and say the cosine of t squared plus, and y is really just the sine of t, so sine of t squared equals 1. And that's where we get our Pythagorean identity of sine squared plus cosine squared equals 1. So we might write this as, I'll just leave it in the same order, cosine squared plus sine squared equals 1. Okay, so there's this whole relationship to the unit circle. Now, if we go into the hyperbolic trig functions, okay, we have a similar kind of relationship, but instead of being related to the unit circle, it's related to what we'll call the unit hyperbola. Okay, so think about the equation of that unit hyperbola. Well, a hyperbola would be like an x squared minus y squared equals 1. And that's what we'll put the 1 in there to make it a unit hyperbola. So imagine if we were going to graph this, we would have vertices at 1, 0, and negative 1, 0. Okay, and then our asymptotes, if we drew our little box in here and connected, they would be, you know, our asymptotes would be these sort of 45-degree lines right here. Okay, and the hyperbola, because the x squared term is the positive one, it's going to open around the x-axis, so our hyperbola is going to look like this. Okay, and just like if I took any random point here, okay, and that point, the x-coordinate was the cosine of t, and the y-coordinate is the sine of t. If I take any point over here, okay, I want to be able to do a similar kind of thing. So here, I could say, well, I know that this point has to be on the circle x squared plus y squared equals 1, and so I get cosine squared plus sine squared equals 1, and that identity has to hold. Well, over here, I'm going to say, all right, the x-coordinate, instead of being cosine of t, this is going to be cosh t, and the y-coordinate, instead of being sine t, it's going to be sinh t. Okay, and it's on the parabola, so it has to satisfy this equation. So we'd like it to be that cosh squared of t minus sinh squared t equals 1. Now, is that actually true? Like, from the definitions that we saw on this page, will that actually work out? Let's see. So notice that the hyperbolic cosine is e to the x plus e to the minus x over 2, and the only difference for hyperbolic sine is there's a minus in there instead of a plus. Okay, so this would be e to the x plus e to the negative x over 2 squared. And then let's see what happens when we do e to the x minus e to the negative x over 2 squared. Okay, so when we square this one, we'll get e to the 2x plus 2 e to the x e to the negative x plus e to the negative 2x over 4. And this one will get e to the x, or sorry, e to the 2x minus 2 e to the x e to the negative x plus e to the negative 2x over 4. Okay, now e to the x times e to the negative x, this is just 1. And this one is also just 1. Okay, so when I subtract these, make sure that that subtraction has to go and be distributed to the entire numerator of the second fraction. So we're going to get e to the 2x plus 2 plus e to the negative 2x, and then we'll get minus e to the 2x, and then a plus 2, and then a minus e to the negative 2x, and this is all over 4. Okay, so we have an e to the 2x minus e to the 2x. Those go away. We have an e to the negative 2x minus e to the negative 2x. Those go away, and we end up with 2 plus 2, which is 4 over 4, which is 1. So yes, indeed, we do get that this relationship, the hyperbolic cosine squared minus the hyperbolic tangent squared, is equal to 1. Okay, so that is our hyperbolic trig identity. Okay, notice that it's different than the circular trig identity. Our hyperbolic trig identity will be different. Okay, so we actually have many different hyperbolic trig identities. We've already seen this one, that the hyperbolic cosine squared minus hyperbolic sine squared is 1. We saw how that worked on this page in the analogy to the hyperbolic and to the unit hyperbola. So let's look at some of these other ones as well. Okay, let's just do if we want to do the hyperbolic sine of negative x, what would that be? Okay, well, going back to the definition of hyperbolic sine, we have to take e to the whatever arguments in here, so e to the negative x minus e to the negative whatever arguments in here, so that would be negative x all over 2. Okay, so that means we're going to get e to the negative x minus e to the x over 2. Okay, now in all of our hyperbolic sine, the e to the x came first, so we could rewrite this if we factor out a negative 1. Okay, so then we would have, oh well, that would be negative e to the negative x, and then plus e to the x. So if I just rewrite that as negative, and then e to the x minus e to the negative x over 2, this is just the hyperbolic sine. So this is minus hyperbolic sine of x. Okay, so that proves this identity. And let's go ahead and do this identity. Okay, so if I wanted to figure out what 1 minus the hyperbolic tangent squared was, okay, I would do it probably similar to how I get these other Pythagorean identities with the circular trig identities. So I would start with the hyperbolic cosine squared minus hyperbolic sine squared equals 1, and then divide everything by hyperbolic cosine squared. Okay, so this is obviously 1. I have hyperbolic sine over hyperbolic cosine. That one is hyperbolic tangent squared. And then I have the reciprocal of hyperbolic cosine, which is hyperbolic secant. And that will be squared. Okay, so that's how we get this one. And there's other ones listed here. Some of those will be exercises for you to do in homework, but you can see that the identities are similar to the identities that we know, but just some slight differences, so be careful. Like notice here, remember with the sine of a sum, we see that sine, cosine, cosine, sine, right? So, and for the cosine, we see cosine, cosine, sine, sine. So it's the same kind of thing that we saw before. So they're very similar, but there are just ever so slight differences. So just be careful. You know, the signs are going to be a little bit different in these Pythagorean ones because of this minus in the middle instead of the plus. So those are the ones you have to kind of be careful for. Okay, so the graphs of the hyperbolic, just the basic ones of hyperbolic cosine, hyperbolic sine, and hyperbolic tangent are given here. And notice that hyperbolic cosine looks kind of like a parabola, but it's not a parabola. Okay, so just so it might show up in mathematical models where you might be expecting to see a parabola, but actually the best model is a hyperbolic cosine. Okay, so the most famous application of hyperbolic functions is the use of the hyperbolic cosine to describe the shape of a hanging wire. Okay, so if you have like two poles with like a telephone wire or some kind of a cable hanging between the two poles, then it will take the shape of a curve that's represented by some constant plus a constant multiple of the hyperbolic cosine of x divided by a. Okay, and this is called a catenary curve. Catenary comes from the Latin word catena, which means chain, because it's like a chain hanging from two, attached to two poles someplace. So you'll see these catenary curves all over the place. Now, in lots of architecture and bridges and arches, okay, a catenary would be just like this hanging chain between 2 points, but you invert that, and all of a sudden this looks kind of like a bridge. This catenary looks like an arch. In fact, the arch in St. Louis is a catenary curve. I don't know if you've ever visited that, but you've probably seen pictures of it. Okay, and so that is a catenary. Just a quick Google search will show you other examples of catenary curves. So if you were to kind of draw a line through the middle of all your teeth, it's a catenary curve. So inside your body, your teeth, your jaw are put together as a catenary curve. This is an example of a greenhouse, and the shape here is a catenary curve. And I'm sure there's other tents and things that are similar in nature to this greenhouse that have a catenary in them. Okay, so we see these hyperbolic functions actually showing up all over the place. So it's not like, well, these are so rare, why would we ever talk about them? They are actually pretty common. Okay, so of course one of the things that we're going to want to do in calculus is find the derivatives of such things. So let's work on finding the derivatives of the sinh, cosh, and the hyperbolic tangent. So the derivative of the hyperbolic sine, well, that would just be the derivative of, now let's look at its definition. So remember, hyperbolic sine is e to the x minus e to the negative x over 2. Okay, so that 1/2 could come out front. I just have a 1/2, okay, times the derivative of this difference. Okay, the derivative of a difference is the difference of the derivatives. And so the derivative of that would be e to the x minus e to the negative x times the derivative of negative x, which is -1. Okay, and so we get e to the x, and then minus is plus, so this is plus e to the negative x, and this is all over 2. And what is that? Well, the one with the plus in the middle is the hyperbolic cosine. Oops, I forgot to put an x in there. So that means that the derivative of the hyperbolic sine is the hyperbolic cosine. Okay, what about the hyperbolic cosine? Well, we'll do something similar. So the derivative of the hyperbolic cosine, the only thing that really changes is that we're going to put a plus in there. So that'll be the derivative of e to the x plus e to the negative x over 2. So when we take the derivative of that, we'll have 1/2 of, and then the derivative of e to the x is e to the x plus the derivative of e to the negative x, which is e to the negative x times the derivative of negative x, which is -1. So we'll get e to the x and then minus e to the negative x over 2, and this is just the hyperbolic sine of x. So that means the derivative of the hyperbolic cosine is equal to hyperbolic sine. Now notice this is different from the circular trig functions. Okay, so for this one we would have a negative here, and this one would just be plain. Here, there's no negatives in either of them. Just the derivative of the hyperbolic sine is hyperbolic cosine. Derivative of hyperbolic cosine is hyperbolic sine. Okay, and let's look at the derivative of the hyperbolic tangent. Okay, well that one's just going to be the derivative of the hyperbolic sine over the hyperbolic cosine. So we'll have to use the quotient rule. So the derivative of a quotient is the denominator times the derivative of the numerator. Well, the derivative of hyperbolic sine, remember, is hyperbolic cosine. Okay, minus the numerator times the derivative of the denominator. The derivative of the denominator is just going to be hyperbolic sine, all over the denominator squared. Okay, now remember that this is going to be hyperbolic cosine squared minus hyperbolic sine squared over hyperbolic cosine squared. And the identity for hyperbolic cosine squared minus hyperbolic sine squared is 1, because it's related to the hyperbola, right? There's a difference for the hyperbola. And so the derivative is then the hyperbolic secant squared. So the derivative of the hyperbolic tangent of x is equal to the hyperbolic secant of x. So again, we see very similar to what we saw with the circular tangent. Yeah. All right. So the derivatives of all of these hyperbolic functions are given here. I mean, we looked at these three. You can do the other three as well, just using the quotient rule. We'll leave that as an exercise to the student, but they're done in a very similar way. So let's say that we know these are what the derivatives are. Let's just do an example of how we might go about doing a derivative where we have to actually use the chain rule. Okay, so we want to take the derivative of the hyperbolic cosine of the square root of x. All right, so this is our outside function, and this is our inside function. Since we have a composition of functions, we'll always work from the outside in. So what's the derivative of the hyperbolic cosine? Well, that would just be hyperbolic sine. So we do the hyperbolic sine of whatever function is on the inside times the derivative of the inside function, right? So the derivative of square root of x is 1/2 x to the negative 1/2 times the derivative of x, which is just x, which is just 1. Okay, so we might write it like that, or probably we'd write the hyperbolic sine of the square root of x over 2 square root of x. Okay. All right, so that's our introduction to hyperbolic functions, and next time we'll look at the inverse hyperbolic functions.